All right, welcome back to operating system. So I forgot my camera, so I'll save you from having to look at me on the recording today, so that'll be nice. So today, the first actual content where you'll need to understand everything today. The rest of it was all set up. So we know what a process is now, so today we'll figure out how to create one. So remember, when we were talking about processes, they were an instance of a running program. I could run the same program more than once, even at the same time. We know that within our process, we have virtual registers because every process thinks it has control over the CPU, so it has its own set of registers that don't conflict with any other process that's running. Right, we had that example where both processes were counting down, one was not affecting the other. Because of that, we also argued that they also have virtual memory. Each process thinks they have an independent view of memory, so their stack and their heap would also be on memory. Then we went on and we figured out that, hey, global variables are actually in virtual memory too. That makes sense. They exist as long as the process exists. And, well, we talked about those special file descriptors. And the file descriptors are also part of the process. And by default, remember, we have three open file descriptors, 0, 1, 2, 0, 1, 2, standard in, standard out, and standard error in that order. So when we get into technical terms, so each process contains a process control block, or PCB, not printed circuit board, process control block. That contains all the information about a process. Specifically on Linux, this is called a task struct, and that link is browsable on GitHub. That will just take you to the Linux kernel source code files, and you can read it if you really want. That's the great thing about Linux being open source. Nothing's hidden for you. In it, you'll probably find things that look like some process state, what state it's currently in. You'll find CPU registers, so that's where it saves the registers. That represent the virtual registers for that process. Has all information to do with scheduling, which we will get into later. Memory management information in order to maintain that virtual memory. Some I/O status information, information about the file descriptors basically, and any other type of information it needs to account for your process. So each process gets its own unique process ID called you might think it's called a PID, you could say that. Sometimes we just say PID. So whenever I say PID or PID, which I will probably never say, that means a process ID. And each process gets its own unique process ID when you create it, and it doesn't change as long as that process exists. So here is a state diagram. We kind of like state diagrams. Maybe we don't. Well, this is the state diagram for the lifetime of a process. So whenever you start a new process, it gets in this created state where the kernel initializes it, sets up all that virtual memory stuff, which we will figure out how to do later, and gets it ready to execute. Now, before it gets ready to execute, whenever it's done being set up, it gets put on this waiting state. You could also rename that to ready. The textbook might rename that to ready. If you want to call it ready, that's fine. It's just able to execute, but it hasn't started executing yet. Then you'll notice that there's two lines here between waiting and running. So at some point, your kernel is going to decide, hey, I want to run this process. It will assign it to a CPU, and it will start executing, and it will just start running until it decides that, hey, it's had enough time, and it puts it back in this waiting state where it doesn't have to execute anymore. Eventually, your program might go through this cycle a few times, and then eventually, whenever it's running, it will transition to this terminated state, in which case that process is done. Does anyone remember the system call we had to use that would probably represent going from running to dead? Yep. Close. One thing is kill. Yep. Exit. Yeah, exit or exit group. That's the way you exit a process, and that's the only way you can exit a process. So going from running to terminated is that process actually calling exit. Then you might notice this weird thing where it goes from running to blocked, and we got a question for that. So running for blocked means that process made a request, and it has to wait. I can't execute it because it's waiting on some information. So you might make a request to a network or a request to a file or something like that, which is really, really slow. So if I try and write some information to the file through a system call, well, it's not going to complete immediately. Your kernel is going to put it in this block state, and that basically just means, okay, this process is waiting for something to happen. I can't start executing it yet because it's waiting for some operation to complete. And if it's writing a file, well, that's slow. It would probably have to wait here for a while. And then whenever it's done waiting for that operation and the kernel knows it's done, so like we're writing to a file, then it will transition to this waiting state or ready state, in which case it can get executed over and over again. And yeah, another comment, can I exit a process by unplugging my PC? That won't exit it, it will just kind of end. Yep.
So like, if you need permissions to run a process and you deny it permissions, would it have to go through the waiting and running cycle to terminate, or it can directly go to terminate?
So if you deny a process from being created, it would just never come up here because it would never get in created, right? If you don't let things get created. So it would never make it to this state. So this is, they're created and they're running. Yep.
Could you go through like the running and waiting cycle again?
So the running and waiting cycle is running just means it's actually executing. And then at some point, the kernel might decide that, hey, that's executed for long enough. I'm going to start executing another program. So it'll essentially stop executing it, put it in this waiting state, and then run something else. So something else will be running during that time. Yep.
So could you explain like how it gets blocked?
So how it gets blocked, block just means it's waiting for some I/O operation or something that's slow. So it made some request, and that request can't be done immediately, so the kernel has to just say, okay, I can't run you anymore because I'm waiting for something to happen. That's basically what blocked means. Yep.
So you mentioned that after running, when it's running for a specified period of time, then it goes to waiting. So
Yep.
Is this specified period of time constant for all processes?
Yeah, so there's a question. I said, hey, it goes from running to waiting after some time. And we'll get into that when we get into scheduling. So that's a whole nother topic that will take us a week. And you could do that, yep.
Sorry, could you explain the difference between blocked and waiting? Because it's kind of unclear.
So yeah, another question, what's the difference between blocked and waiting? Waiting means it can execute, it just hasn't had the opportunity yet. Blocked means even if the CPU is not doing anything, I can't run this because it's waiting for something and it's blocked. Right, yeah.
If a process is stuck on block for a long enough period of time, will it be auto-terminated?
Yeah, that's a good question. If it's stuck on blocked for a long enough period of time, will it be auto-terminated? And the answer to that is no. So we'll get into this and see it when we get into more process management stuff. But so far today, that whole created thing, that's where we're going to be focusing on today. So we're just going to learn how to create a process. Things will get a bit weird. All right, this is your primer for lab 0 or lab 1. So accessing process state is doable on Linux through something called the proc file system. So there will be a special directory at the root of your drive called /proc, and it just looks like a normal directory that has files in it and other folders and things like that. So on Linux, this /proc directory represents some internal kernel state because it doesn't want to create system calls for literally everything. It just presents some information as a file that you can just read from and write to if you have permission to. So they're not real files, they just look like it, which is kind of fun. And every directory in that, every directory in that proc that starts with a number, that is a number, represents a process. So each process gets its own folder in that directory. And within that folder, there is something called a status file that contains the state of the process. And that's what you'll be using for lab 1. So in lab 1, you're essentially going to make a process monitor. So if you've ever used Task Manager or Activity Monitor or something like that that lists all the running processes, well, you're writing something that will list all the running processes on Linux, which is kind of cool. Yep.
folders or files in the /proc directory are not numbers?
So one instance, there's /proc/CPU info that will tell you information about like your CPU that you're currently running on, stuff like that. You can poke around in that directory, all kinds of information in that. Yep.
If you kill a process, is it removed from the proc directory?
Yeah, that's a good question. If I kill a process and it no longer exists, does it get removed from the proc directory? And yeah, the kernel will remove it from the proc directory, so it won't exist anymore. Okay, so about creating processes, this is where it gets fun. So you might think it might be pretty easy. I just say what program I want to execute and say, go create a process for that. Well, that's something you could do. So you could make that a system call, tell it that I want to load that program into memory, create a process control block for it, a new process, and start executing it. And that's what Windows does. So there's a system call called create process that does probably what you expect. On Unix, like Mac OS or Linux, that is not true. So Unix decomposes this into two more flexible abstractions, so it's a bit harder to create a process, but we'll see why that might be advantageous. So on Unix, instead of creating a new process, what it does, which will start off being kind of weird, is it clones the current running process. So what it does is it will pause whatever the current running process is, copy its process control block to a new one, which reuses all the information from the process, including variables. The new process also gets its own virtual memory, so it's actually completely independent, but it looks exactly like the process that it got cloned from. And the only way to distinguish between the two is with a parent-child relationship. So it maintains this relationship throughout. We'll get into this relationship more in the next lecture, so you don't have to worry about it too much for now. But what that basically means is whoever initiated the call is the parent, and the new process is called the child because it essentially gave birth to it, kind of. So you can think of it that way. And we have a process is blocked like a mutex. We will get into mutexes much, much later. Yeah, much later. All right, so since we create a clone of it, well then, now that new clone process could load a new program, and we'll see how to do that, or it could just continue executing the process and then you split it off into two. Maybe you can make the new process do half the work and the parent do the other half of the work, and hopefully be 2 times as fast, something like that. And we'll get into reasons why you might want to do that. But first, let's figure out how to create it. So you might think the system call is called clone. Well, it is, but for reasons, the API you will use to actually clone a process is called fork. And it creates a new process, which again is an exact copy of the current one. So you might see it returns an int, and it takes 0 arguments. And its API is as follows. So it returns the process ID of the newly created child process. So -1 means it didn't create a new process and it failed. And otherwise, this will look like it returns twice, because after it returns successfully, it will get 2 different return values depending on if you're the old process or the new process. And this is where your life gets complicated. So fork in the new process gets an ID of 0 to represent that, hey, it's the newly created one. And the parent gets the process ID of the child. So it gets the process ID of the newly created process. And we'll see that it's also called the parent because it will also have to take care of it in some respect. So the naming kind of makes sense, although this is where your Google searches kind of get weird, because you'll be like, how does the parent kill the child? And then they'll be like, you'll be on some list. Yep.
So if you're not passing anything into this function, how does it know which process to duplicate?
So yeah, the question is, if I'm not passing anything, how does it know which process to duplicate? And the answer to that is it duplicates whatever called it. So if you called fork, so in main, if the first thing you called fork, it would duplicate that process. So we'll see an example. Most of this class is like dedicated to code examples because it will probably hurt and you'll tell me to do odd things and we'll see it. So yeah, after this point, two processes are running. They can access the same variables, but they're completely independent. And the operating system or the kernel will do some optimizations to make this really, really fast that you will understand later. Yep.
Could you go back to the previous slide? I didn't understand the in the child process or in the parent process part.
Yeah, so you might, yeah, so that's okay. If you don't understand the in the child and in the parent, we'll get to it. So I'll actually just show you an example and we'll go through it. And it'll probably be clearer than me trying to explain it. Looking at code is always better. So on POSIX systems, you can always find documentation using man if you really want, so which is short for manual. So today we're going to use fork, and if we have time, hopefully we have time, we'll use exec VE, and then next lecture we'll use wait. But you should be able to do like man fork, man exec VE, and man wait, and you can get some documentation for it because it's full of fun little caveats that will make your life more difficult. But let's just dive right into an example. So here's fork example. So in this example, at the beginning, it has a main. Whenever we execute this program, it will start executing at main. Our lives haven't changed yet. And the first thing it's going to do is called fork. Now, if fork successfully returns, there's a new process created that is an exact copy of whatever started executing main. Luckily, it didn't really do anything beforehand, but now there is two processes running this program. So first, we have an error check here that sees if it failed. So if it failed, there wouldn't be two processes. It would just have an error code, and this would exit immediately. Otherwise, one process is going to go into this branch because its return value from fork is 0 to indicate it's the child. So it would say printf. So I just print the return value from fork, so hopefully it's 0 because that would make sense. And then there is a system call here called getPID to get the process ID of the current running process. And then there's also another one to get the PPID, which is the parent's process ID. So you can see that there's this relationship that is enforced. Now, in the parent, well, we can get the return value from fork. It's not going to be 0, and it should be the child's process ID here because that's the new process that got created. And then, of course, the parent is going to have a process, or the parent is going to have a parent as well. So we could also print that PID just to make it fun. So, oh, and we have good questions and we have lots of forks. Okay, we can try breaking stuff. I'll probably wait till the end of the lecture for that. So here we go. So if I execute this program, I should hopefully see all of these lines. Oops. So I execute it. I can see that in the parent, it returned PID 2816 from fork, which lines up with the child's process ID. And the parent's process ID is 2815. And its parent is 1726. And you can see here that the child's parent ID is 2815, which is the parent. So that makes sense. But here you can see that lots of fun things are happening. So it looks, if you don't know what fork does and that creates a new process, it looks like we're going into both of the if branches at the same time, which is not true, that your world still makes sense. Only one process is doing it. There's two processes. Yep.
I think the doubt is coming, like, let's say the parent process calls fork.
Mm-hmm.
So for the first time, fork returns the parent process ID.
Yeah.
Then it returns 0.
Yeah.
Then it returns the child's process ID?
No, so here, let's,
What's the sequence?
so here, I will try and break it down a bit more. So let's go to iPad. First time breaking this out. Okay, so let's say we begin execution at main with process ID, what was it? It was process 28. So something created a new process that started running this program, right? So it would start executing. Here, we know that's a little bit of a lie, but it has to load the standard C library and all that. But for our purposes, it can still start executing at main. So that process is created, and it currently hasn't called fork yet. So what's going to happen is it calls fork. So at the time it calls fork, it kind of gets paused before it returns from fork, and we create a new process. In this case, it was process ID. Here, I'll do a different color. Process ID 2816. So it will be an exact copy of this at the time of the fork. So it will also be here, and it hasn't returned from fork yet. So it's an exact copy. Neither of these have returned from fork yet, and now I have two processes that look exactly the same at this point and this point only. So right after this, they're going to differentiate because fork for the original one will return 2816, and fork for the new one is going to return 0. So right after the fork, we don't know exactly which one will execute. That's like a whole nother can of worms. But they will both be right after the fork and have different values for that PID variable, because it's going to return, and now they're independent of each other, and then they assign that PID variable to 0 or 2816. So now there's two things executing. So, yep.
So for example, if you had instructions before the fork, the child would not execute those instructions, right? Like it would start executing instructions after the...
Yeah, so that's a good question. If I had instructions before the fork, then would the child execute them? The thing for that is it's a copy at the time of the fork. So if the parent executes them before that, it'll be executed in the other one because it'll just copy it at that point. So we'll see an example. Yep.
So if the fork fails, does the parent process keep running? Or
Yeah. Yeah. So if the fork fails, there wouldn't be a new process created. So the one in green there wouldn't exist. And the original, there'd still only be one process, and it would return -1. And we wouldn't have two. Yep.
What stops the program from continuously repeating fork? Because it's going to copy the entire function, right? So
No, so it copies it during the call and then returns from it. And then it just continues executing. So both of these, at the time of the fork, it gets cloned. And then right after that, no. It will not clone the actual fork call. The fork starts to clone. So the fork makes the clone. Yeah, then some questions. What we'll call is fork to fail, lack of resources. Someone said what happens if a fork forks a fork? Then yeah, we'll see that. That's bad. Yep.
what's PID-_T?
Oh, yeah, so the question is, what is PID_T? So PID_T is just supposed to mean the type of a PID. It's an int.
Okay, but what I'm confused is, there are two returns of fork, right?
Yes,
And they both get returned into PID.
yes.
So PID's value will always end up with a 0, or always end up with a 0, right?
No, so it depends. So right after this fork, the processes go their separate way after the fork returns. So one of them will get a return value from fork and then assign it to its PID variable, and the other will get its return value and assign it to its PID variable.
Oh, the process's own PID variable, it gets the return from fork and assigns it?
Yeah, so right after the fork, they go their different ways.
Okay.
And their different ways is the next thing both of them will try and do is assign PID, right? Because it does the call first and then the assignment.
Yeah, and they both get it from their own
Yes, yeah, yep.
So after fork executes, will both programs have the same, like all the same if statements and else stuff? Will it get copied to the child?
Yeah, so that's a good question. So if they're exact copies, do they also have the same if statements and everything? And the answer to that is yes, they have the same instructions, just one. So let's see here. So this original one that is currently here, well, it would assign 2816 to PID, and then, whoops, what did I do? And then it would continue execution as normal. So same thing from top to bottom. Whoops, I took some of that. I'll fix it. So it would check if PID is equal to -1. It isn't, so it would hop over. Then it would check if PID is equal to 0. It's not, so it would go into this else, and then it would print this, print this, print this, return, and then end eventually. And that's before the child executes. So, whoops, I stole another piece of it. And then when the child executes, well, same thing. It would assign 0 to its PID, then go through the if branch, check, oh no, it's not -1. Go here, is it 0? Yes, and then print, 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 then fall out, and then return 0, and then end.
In this bit, how do we know which fork actually runs first? Which process runs first?
Yeah, so the question is, how do I know which one actually runs first? And the answer to that is, you don't.
So it's completely random.
It's completely random. It will likely be the parent, but not always. So right now I have this call here to sleep to make sure that, actually that doesn't make sure of anything. Yeah, so that doesn't actually do anything. Oh, right, that's why I have it. Okay, so that doesn't guarantee anything. It just guarantees that my console doesn't look weird. But if I run it a bunch of times, there, it's in, whoops. So if I run it a bunch of times, I can get different orders. I don't know which one's going to execute where. That time when I ran it, the parent line that printed what it returned happened first. Then the child happened for 2 calls. Wow, that one's a good one. And then the parent went, and then the child went, and then the parent went. Yep.
So is this technically multi-threading?
So there's a question, is this technically multi-threading? And the answer to that is technically no. Technically, we'll figure out what this actually is. It's very, very much related to multi-threading, but not quite the same thing. Yep.
Yeah, so does the return value for each of the process become that process a new PID?
No. So process ID, yeah, the question was, the return value from fork, does that become the process's new PID? And the answer to that is no. So your PID never changes. So like here, as long as the parent is executing, its PID is going to be 2807. It could create multiple forks over and over again. It's never going to change. So it stays constant for its life.
So what does the return value actually do then?
So return value in the parent tells you the process ID that you just created. So it tells you the process ID of your child, and for the child, it tells you that you're a child. Yep.
You said that when you fork the child, say there are previous instructions before the fork.
Yeah, so we have some questions about previous instructed. Let's go through this because we'll see some more examples. So what if I had some more stuff? Int x equals 42, something like that. So if I have that, and I do, I don't know, let's see, x equals x. So in this case, what should I expect to see? Yep.
42 and then all the parent stuff, and then 42 again, and then all the child stuff.
Yeah, 42 and then all the parent stuff, and then 42 and all the child stuff. Well, let's see, because that might not be true. In this case, it was true. So we got x, then all the parent stuff, and then x, and then all the child stuff. So because fork happened before, well, it would be an exact copy, like an exact copy. So the new process would also have an x, and it would also be 42. And after that fork, as long as it's successful, there's two processes, so both of them will print that line. Yep.
What if the print statement and the fork line switched?
So what, here? Like what if I just did this?
Yeah.
All right. Anyone want to guess what happens here? Yeah.
42 parent child?
42 parent child. And how many 42s? Just one? Just prints once. We got just prints once. So hopefully, so yeah, just prints once. So that happens before we fork. So there's only going to be one process running. Whatever just created that fork example, it creates a variable, prints, and then it splits off into two. Yep.
How come the print thing is like the order that it comes is not deterministic?
Yeah, so there's another question. Why is the print order not deterministic? And the answer to that is because there's two processes running and the kernel gets to decide which one runs. And it can make that decision and do whatever it wants. So yeah, it will not make the same decision every time. If it did, then that would be kind of limiting. It tries to just run things as fast as possible. So because I have a multi-core machine, one of them could have been on separate cores and running at the same time. Lots of things could happen. Yep.
So you tried to use a delay, I think, to make one happen before the other, or I might be wrong about that.
No, so this delay happens every time. It's because my terminal returns back to me whenever the parent's done. So I might be in the case where the child or the parent finishes first and then my terminal gets all messed up. So that's just not to mess up my terminal.
Is there a way to like ensure one runs after another? Or?
Yeah, there's a question, is there a way to ensure one runs after the other? And the answer to that is yes. We will not learn how to do it yet. You will learn kind of how to do it after next lecture. Yep. Yeah, so in this case, the child process didn't print the value of x because the original process came, it started executing main, it created a local variable called x, it printed, and then it forked after the print. So now there's two processes after this time. That print already happened, so it wouldn't happen in the child. Yep.
When does the copy pasting end? So like it starts from PID from the fork line, keeps going down. When does it stop?
So the answer, when does it stop?
Yeah,
Like what?
Like for example, it starts, like it copy pastes, starts from the fork line, and then takes everything below it and then copies it, right?
So it copies the current process at the fork.
Okay, and like the instructions that it has for the current process.
Yeah, the instructions, literally everything. They look exactly the same.
So the instructions are everything that starts from fork until?
So the instructions are literally everything that's loaded into memory. It's the whole program.
Oh, so until return.
Yeah, the whole program will be in memory still.
Everything after fork.
Yeah, the whole thing.
Then
'Cause-
if it's the whole thing, then why didn't we get 42?
So the whole thing will be cloned. It just won't be executed because it already executed it. So like the instructions are just some binary data, right? But at the fork, it's a copy, including the program counter and everything. So it wouldn't go backwards and start executing stuff.
Oh, so it like copies the entire thing.
Copies literally everything.
Everything, but the fork determines from where it starts executing.
Yeah, so the fork is the place where a new one gets created and they start diverging. Yep.
If it will never go to the instructions that are before the fork, then why does it copy everything? It's never going to go to those instructions.
Yeah, so there's a question, if it copies everything before the fork, then why does it copy the instructions that already happened? And the answer to that is, well, we'll get into it. Essentially, it doesn't cost anything. It's free. So, and you also don't know. Imagine if the fork got created in a loop and it went backwards. So it would have to be there anyways, right? Otherwise, you get into this weird program analysis thing and it doesn't make sense. So in order to see that they are exactly the same here, I will create x equals to 42. Whoops. And then after, do I have caps lock on? And then after this here, I will print the address of x. to show you that they are indeed the same. And whoops, wait, did I not compile? Oh, what the hell? Oh, I didn't save. That would help, eh? All right, there. So you can see the address of X for both of them, same thing. It's an exact clone. And why is this possible? Because it's virtual memory. You can even see that, hey, in this one, let's say X equals 1, and the other, we don't care. And then at the end, let's go ahead and print X. So what should I expect to see here? Can I fit it in? No, not really. Yeah.
42 parent 1, 42 child 42.
So I just have the address and then one print.
Oh, yeah.
Yeah, so that was a good guess. It was, let's just execute it. So in this case, I got address from both of them. Don't know what order. This case, it looks like the parent happened completely before the child happened. Did I forget to save again? Yes. Okay, this one's a bit weirder. So the parent happened first, printed the address, then printed its 3 lines. Then the child printed the address, which is the same thing, and printed its 3 lines. And then 42 happened, which should have been the child, because in the parent, it changed X to 1. And so this is from the child, and then this is finally from the parent. Right, and they're independent, so no matter if I get them in a different order, how unlucky will I get? Apparently not that unlucky. Yeah. Actually, that wasn't that much unlucky. Okay, I can't get that unlucky. But they'll print different variables. No matter if that X equals 1 gets printed first, it doesn't affect the other process because they're completely independent, even though that address looks the same for both of them, but each process has its own virtual memory, right? All right, any more fun questions about that? Yep.
What would happen if you call fork twice? Would you have like 4 processes?
Yeah, so we got a question. What happens if was that your question too? What's your question?
If the virtual memory, if we get the same address, how comes it's different? I know it's virtual memory, but still the same physical base.
So the question is, why do I get the same address for both of them, even though it's the same physical place?
I mean, it's the same address because I think because the same physical place on the ROM.
No. So these are not physical addresses. These are virtual addresses. And because I can change one without changing the other, no matter in what order they happen, it means that they correspond, those virtual addresses that look the same in both processes actually correspond to different physical addresses. And we'll get into how to do that mapping later, but they're independent. Oh yeah, another question, what process is 1726? So let's answer that first. So if I want to know what process that is, what can I do? Yep.
Go to the /proc directory.
Yeah, let's just check it out. /proc, what was it? It was 1726 state, I think it's status. So you get all sorts of cool information about it. Some of it you won't be able to read yet. That's fine. We can read its name though, and there's its name. ZSH, that's our shell. That makes sense because I typed the name of the program to execute in my shell. So my shell created it. Huh. Well, if fork is the only way to create new processes, what did my shell have to do? It had to fork. Whoa, that's crazy, right? It's true. Let's see what we have time to do. So there's another question. What happens if I make something even more fun, like fork, fork? So anyone want to guess what happens there? Yep.
We create like a lot more copies.
Yeah, I create a lot more copies. All right, so here, let's go so let's just run it because it will look weird. And, you know, this is like compile. So I get a bunch of stuff. So eventually, at the end of the day, we know that there's at least 4 processes there. Yeah.
So you know how like fork creates like the same exact program, like in a different process, like separately?
Yep.
So like, how do you create like a process for a new program?
Yeah, so the question is, how do I create a process for a new program? And we'll get into that hopefully at the end. So it's another call. Yep.
Can you scroll up a bit?
Terminal?
So the parent's ID is 4064, and then the child's is 4065, and then where's 4067?
This one. So this would be more like, hey, an example question. So you can figure this out. We won't yet. We can go through it later, but we still have some more stuff to get through. Yeah.
So it's like you have parent, first child, and then another parent and the second child. Is that it?
Yeah, so basically what will happen here, if I put another fork here, whoa, my writing's terrible. So if I put another fork here, say, we can say that. So some process, let's say process 1 to make it easy, is going to start executing main, and then it's going to fork and create some process 2. And I can draw an arrow that says what the parent-child relationship is. So P1 created P2. Now they would be both exact copies at the time of the fork. Not much is going on. This one would get PID equals to 2. This one would get PID equals to 0. And then they would both fork again. So you don't know what order they're going to happen in. So this one would create process like 3. And then process 2 would create process 4. And it would look something like that. Yeah.
If you put the fork function call in a for loop,
Oh, God. All right, so that will probably ruin my next lecture. Oh, well, whatever. So let's say, well, 1.
No, wait,
What does that do?
infinite copies.
Yeah, so first time through the loop, how many copies am I going to have? 2. Next time through the loop, how many copies am I going to have? 4. Next time through the loop, how many copies am I going to have? 8, 16, 32, 64, 128. Things probably get real bad real quick. And that is when fork starts to fail because, well, that'll grow pretty fast. The PID is an int, so eventually it's going to run out of space to even give me process IDs because it'll run out of numbers. If I don't run out of memory, we'll run it before, okay, so I'll set up another thing and then we'll run it and probably ruin the next lecture, so they'll thank you. So let's quickly go through this. We'll have more time next lecture to play with these. So there's a question, how do I create a new process? Well, there's another system call for that, and it's called Exec VE. So that replaces the current running process with another program, resets the whole process control block, and starts executing that program. So it has a bit of a different API. It needs a path name, which is the full path or file name of the program to load and become. And then its next argument is an array of strings that will eventually get passed to main for argv, and then some environment variables that we can have this handle, and then it will return an error on failure. And it doesn't return if it's successful because this process becomes another one. Yep.
Does exec v like replace the parent or the child?
So exec VE replaces whatever process called it. So if I go back to this example, if I put, so if I put exec VE here, the parent would call it. If I put it here, the child would call it. If I put it somewhere else, they would probably both call it. So let's quickly get into the example so I can say we did it and then break stuff. So here's how that works. So again, if I start executing this, it becomes a process that starts executing main. Your life is the same as it was at this point. It should do this printf, and then here are the argv. I'm just going to have it run ls, and I'm not going to set in any environment variables because I don't care. And then for exec VE, I'll say this is the full path of the ls program, and I'll give it the argument and the environment, and then I'll check its return value. So if it returned -1, it means it failed for some reason, and if it doesn't, well, this line should never get printed because the process just becomes ls. The whole process control block gets replaced. The process doesn't exist anymore. So let's go ahead and see that. So you can see here when I run it, it says I'm going to become another process, and then it does the same thing ls does. So it just shows me everything. All right. So why could it fail? Well, I mean, I could just give it an invalid file name, LSS, something like that. In which case it's going to fail. It's going to say no process or directory. Yep.
Is there a way to get the process ID for the new process you created for that?
So the question is there a way to get the process ID for the new process I created? So in the exec VE example, I'm not creating a new process. I'm just becoming a new process. So the PID would stay the same. Yeah. All right, so we still got 3 minutes, but let's see how this works. So go to code, fork example. All right, so I have this loop. We kind of said that it should go 1, then 2, then 3, then 4, and then probably break. Well, let's go ahead and execute it, and hopefully I'll have time to fix it. I didn't save it again. I keep doing that. Okay, compile. All right. Oh, I'm scared. Someone else want to hit enter for me? I'll do it. Uh-oh. Oh, I opened a new terminal. Oh, it's not opening. Oh, I can't even type anything in it. That's the lecture. All right. Just remember, pulling for you. We're all in this together, and someone can come fix my laptop. Oh, yeah, see? Look. Terminal process failed to launch. Native exception. Fork failed. Lots of bad things.